All yours, Gordon.
All right, let me get my screen up here. Hold on. All right, let's see. Everybody should be seeing my screen, right? Yep. Tom?
Looks good, Gordon.
Okay, good. So, hello. My name's Gordon Rosner. I'm the president of the East Valley Astronomy Club, and welcome. Welcome to October's virtual general meeting. So, as usual, live long and prosper, everybody. And hey, by the way, to prosper, living long is up to you, but to prosper is continue to join us every month for these meetings in which we have fantastic speakers, and certainly we have an example of one today. So introductions, I always put this on up to let you know who the current leadership team is. Of course, I'm the president. Tom is the vice president. He's the one who does the behind the scenes computer work for us on making these online events possible. Our treasurer, Brooke Schofield, handles the money. Our secretary, Wayne Thomas, takes the notes and the minutes so that we have something in our history ledger on board meetings, meetings like this. Any meeting that goes on, then Wayne does the minutes for us. The board members at large. Now, who are these people? There's 5 of them there. And what they are is they are folks who keep their fingers on the industry for us. And they bring up issues whenever we have board of directors meetings. They vote on possible improvements to the club, that sort of thing. Now, the administrators, also keep in mind, the administrators are not elected folks. They are assigned. So people who are interested in doing those jobs, they come to us and let us know. And then the board determines whether, all right, great, we'd like to have you on board. Fortunately, we have a great group of administrators right now. And they're not elected, so they're not a part of the general elections that are coming on up. And down at the bottom left, always the most important member of the club is you. We are now into officer elections, and we're accepting candidates right now. And I mentioned this last month, also mentioned it in the newsletter, that next month, October, or the November meeting, is actually when we do the voting on who is going to represent the club. So today it's open, and it will run through the end of business on Monday. So what you can do, if you're interested in any of these positions, you can just go to our website, that website, way down at the bottom, near the bottom. You can just, there's contact the president link in there, and you can just send me that you're interested in one of these positions. Because remember now, you know, if you're chomping at the bit to be one of our officers, do this before Monday, during Monday, before Monday ends. And this is your chance. This is your chance to be a part of the EVAC leadership team. So anyone who has the slightest inkling, jump on in. We are in a great situation in that we have processes now, entrenched processes, very good processes, pre-pandemic and current pandemic. So as we transition, hopefully, as we transition into a post-pandemic, get back together, celebrate, hoorah, yay, have a great time like we used to, face, we have procedures in place for that. So anyone who is interested, don't let that slow you down. And plus, previous officers always help current officers who step up. So remember, voting will be done during the November general meeting, which is next month. And let's see, the positions open, they all are open. Remember now what's happened is we've gone 2 years with the same people because of the pandemic situation we've been in. So the president, of course, kind of runs the show. That's me. I got the easiest job of anybody because all I do is make sure everyone else does their job. And we have a great group. They all do a fantastic job. So I have an easy job. The vice president, that's Tom Mosden. And he takes over. If I can't make it for some reason, then obviously as vice president, he would take over. He helps out in getting presenters for our monthly meeting and various other things. He's a computer whiz, so he helps us set up these meetings. The treasurer, of course, is just like the treasurer of any club. He takes in the money, which is donations or membership dues, balances the books, puts the money in the bank. If the board of directors decides to buy something, then the treasurer, of course, writes the check. If it's a big check, then the treasurer and the president has to sign the check both. And all 5 board of directors at large is up. All 5 of them are up. So anyone wants any of those positions, they are open, jump on in. Look at the current EVAC October newsletter, the one that's out now that's available on our website for detailed positions or descriptions of the positions. And now also you can go to our club webpage. And at the very, very bottom, last line, maybe second to last line on the landing page, the main page, it says bylaws. Click on that bylaws link, and our policy and procedures and our Constitution are in there, and then you can read in detail on what the responsibilities are. So again, remember, voting is next month. So if anyone is interested, or I should say, all of those who are interested, you've got to let me know by Monday evening. So club news or club O's, always put the same slide basically. Greco remains open for private star parties. Greco is our observatory, picture up there in the upper right. Sunday through Thursday evenings, as we have been doing for months now. They're normally small family gatherings, and anyone interested in a private viewing can go in our website and the Greco page. You fill out a request and then get on the schedule. Now, it's getting exciting, folks, because what we're doing now, the board of directors, is we're going to start dipping our toes in the water. And Greco is going to be open the next 3 Saturdays for the general public. And, we're really not announcing this to the world. We get a lot of walk-bys in our observatory. And what we want to do is just open up, and we have safety measures in there and hand cleaning stations. Our operators, we're making sure that they're comfortable with the surroundings. So it's kind of like a test of being open to the public. So if you happen to be walking by Greco at the Riparian Preserve on tomorrow or the next 2 Saturdays in October, you can sneak on in there and look at the equipment, and Claude will explain the objects that we're looking at. And all other EVAC personal contact events are still canceled. We thought we would be back to in-person stuff, and we took a downturn in the pandemic, so we're looks like we're starting to climb out of it again, but we really don't know when we're going to have in-person events yet. So stay tuned. We definitely will let you know during the meetings and in our newsletter and on our webpage. And continued member presentations. just remember, this is every month I show this, is anyone wants to make a presentation, 10 minutes or so on any astronomy subject. Maybe they visited an observatory or they're building a telescope, whatever it is you're certainly welcome to make a member presentation and a member article. Kind of a one pager. If you want to write up something about your wanderings around, your adventures in astronomy that you'd like to share with everybody, by all means, let me know through the website, and we'll make sure that we get it all polished up for you and get it in the newsletter. And remember that these monthly meetings are being recorded, and the link is provided on our EVAC website. So if you missed this one, you had to leave early, you got friends, family saying, oh man, Tyler did a fantastic job of presentation, then you can view this later on just by clicking on the link in our webpage. So our next EVAC meeting is Friday, the 19th of November at 7:30 p.m. The main presentation will be by Jeff. He's a science journalist and author of many astronomy books. You may recognize that name. And he's going to give a presentation on peculiar galaxies, touchstone galaxy classification. What makes a peculiar galaxy peculiar? That should be interesting. So what we'll do now is Tom Osden has a little quickie for everybody right now on something that's happening tomorrow that should be of interest to just about everyone. So Tom, take it away. Let us know.
All right. Let's see. So this is an announcement that I was asked to make by Rick Alling at ASU. And he's looking for some participation help, and you don't have to leave your backyard to participate. So Saturday, October 16th, tomorrow, 7 to 8:30 p.m., we'll be live broadcasting via a webinar celebrating International Observe the Moon Night. Many people in EVAC have participated in the past, and they had or like in last December's conjunction with Jupiter and Saturn. So again, the format is that if you have a telescope with a camera on it, you hook that camera up to your laptop to display the image on the laptop. You dial into the meeting, the Zoom meeting, and then you can share your screen and show what your camera is capturing about your current view of the moon. And if you don't have a camera, you can also just point a telescope camera, you can point your Zoom camera at your telescope and show people what you use to observe the moon. Let's see, they're expecting 300 to 350 people. So when Rick has a very large audience base, and he gets really great turnout, and it's really educational for the community. So if you'd like to do it, or you know somebody who might want to participate, he's a couple people short. He'd like a little more help. And down there at the bottom is his contact number, 480-727-7797. I'll put that in the chat. Or if you want more information, just send me a message in the chat or send me an email message. So that's the request for help and observe the moon event tomorrow evening. And that was it with my announcement.
Okay. And then let's see if I can get back up on board. In fact, let's see. In fact, Tom, we'll just kind of segue right into you, because you'll be introducing our next speaker. So stay as is there, Tom.
Okay, let's see. All right, I've got my info now. Okay, yeah, it's my pleasure to introduce Tyler Richey-Yowell. And Tyler's in her 5th and final year of her PhD at ASU. You're like moments away from graduating. And during her academic career, she has been able to work with data from optical telescopes ranging in size from 4.2 centimeters. That's not a typo. It's called the kilodegree extremely little telescope. KELT.
Real name.
Yeah, that's I had to look twice at that, like, oh yeah, okay, the name helps. Up to the 10-meter Keck. Wouldn't that be fun? A 10-meter telescope, just in our dreams. And radio dishes that are even larger, like the VLA. And the only wavelength regime Tyler has not worked on is in the gamma rays, but she's hoping to complete the electromagnetic spectrum at some point in her future. Her PhD research asks the question, how does the ultraviolet environment around K-stars change in time, and how does this differ from solar type M stars? And she uses Galaxy Evolution Explorer photometry and Hubble Space Telescope spectroscopy to form theories of K-dwarf planet habitability. I'm not going to even try and say that again.
Habitability.
Thank you. And I'll turn it over to Tyler. Take it away.
Let me share my screen again. All right, did that share?
Looks good.
Okay, great. All right. Thank you guys so much for having me. I'm going to talk to you about my PhD work from the past 4.5 years. And this has been about understanding the high energy evolution of K-stars. And this has always kind of been with the mindset of what does this actually mean for planetary habitability? And my perspective on the potential habitability of planets around K-stars has kind of changed a lot during my time in grad school. And so I want to kind of lead you guys through my experiences today and kind of have you learn in the same way that I learned, because I think it is kind of a fun story. So first off, I just want to make sure that we're all on the same page about what M, K, and G type stars are. So M stars are the smallest and coolest types of stars, while G stars or solar type stars are like our own sun. And K stars are the stars that fall right in between these two. So a lot of the work that has been done on searching for a potentially habitable planet has been focused on these M stars due to their high planet to star mass and radius ratios, since the star is so small, and also G stars because obviously we have one detection of life there. So it's got to work out for G stars at some point. But K stars have really been neglected in these studies. And so that's kind of where I come in. But I want to see if we can do this Zoom poll first, just to kind of get a sense of what you guys think, just with whatever knowledge you currently have. So I think Tom might be able to share this poll. If not, we can do it more informally. That's okay.
Okay, I've created it and I think I launched it.
Oh yes, I see it. Great. Yeah, so we'll just take a little bit of time to go through this.
These are great to see evolve live.
Yeah, and don't let the title influence you. You don't know whether K-stars are good or bad. So just because I'm interested in them doesn't mean they're good or bad.
How do we select one?
Oh, so you should just be able to click. There's like a little button next to G, K, or M.
Nothing happens.
Oh, well, maybe it goes through on my end because I see most people have voted.
Down on the bottom, it says host and panelists can't vote.
Okay.
Wayne,
sorry, Wayne. We have to stay neutral.
yeah, we have to stay neutral.
Yeah, well, what's really interesting about this, and this is not the way that I would have thought it, it's actually quite even. So most people have voted, and so I'll just go ahead and say that about 40% of people are saying G stars or solar type stars like our own, 35 for K stars, and 29 for M stars. So it's really about even on the board. And so I want you guys to remember that for later when we vote again. Okay, so great. Now that we have that basics, let's talk about life. Ooh, poll is there again. I don't know how to get rid of that. Anyways, let's try this. Okay, ideally, if we had unlimited time and resources, we'd search for life like this. We would discover a rocky planet. We'd check if it's in the habitable zone, which is just defined as a planet at the temperature where water would be liquid. And then if it is in the habitable zone, we go and look at its atmosphere to see if there's molecules that would be indicative that life is there. Right, easy enough. In reality, though, it's not really feasible for us to observe every planet that's out there. So we have to have some way that we can prioritize which planets we actually want to spend the time observing. And true habitability isn't just where life or where water would be liquid, though. There's a lot more that goes into being able to form life. And so the major components that go into this are stellar effects, the components of the planetary system, and the properties of the planets themselves. And of course, each of these can be divided further into subcategories, which can be divided further into subcategories that play a role. So my research focuses on understanding the potential for life from the stellar side. That is, understanding the spectra of the stars, the stellar activity, and the luminosity evolution of the star. So this essentially tells us how much radiation is incident on the planet. And so to rephrase this, in order to understand planetary habitability, we need to know, how does the flux of a host star evolve in time? The most important wavelengths for determining planetary habitability are those at these high energies. And this is because here's where you cause photochemistry to occur in the planetary atmospheres, and you can even damage DNA. And so in this talk, I'm really going to be focusing on the ultraviolet, the UV, in particular the near UV, this region from 3200 to 1700 angstroms. So that's 320 to 170 nanometers. And the far UV from 1700 to 912 angstroms. What happens at these wavelengths is that you can drastically alter the chemistry of the atmospheres of the planets. So here we have a spectrum, so flux as a function of wavelength, and this is of a late K star, and you can see that most of the flux, like there's kind of nothing here, it's very small, and then most of the flux is at this black body peak here in the infrared. But if we actually zoom in on this left side here where the UV actually is, we can see that there is actually flux there even though it's small. And so this UV flux will photodissociate or essentially tear apart the molecules that are necessary for the development of life, such as oxygen or water and signatures that would be indicative that life is there, like methane, ammonia, nitrogen oxide. And the X-ray and extreme UV will ionize the atoms or take off the electrons of the atoms and may cause complete erosion of the atmosphere. And so the atmosphere will just go into space, and so you have no atmosphere left. So obviously not good if you're trying to live there. So even though these features are quite small relative to the black body peak, they are still quite important. So what we really need to know to understand planetary habitability is how this stellar high energy radiation evolves during a time scale when planets are forming and their atmospheres are still stabilizing. Now, wouldn't this be a great question for a starry-eyed first-year grad student to look at? And so that's exactly what I did. My advisor had just completed a project called the Habitable Zones and M-Star Activity Across Time, HAZMAT. And so we decided that I would extend this into the Habitable Zones and K-Star Activity Across Time, or HAZKAT project, and then compared those two. So the goal of the HAZKAT program is to measure the UV evolution of K-stars as a function of age to determine what the UV environment is like while planets are forming around these types of stars. But why K-stars? Like, why do we even care about those? Well, actually, it's because everyone is into M-stars right now. And so the vast majority of the searches for habitable planets are those around M-stars. In fact, all of the habitable zone planets that have been and are expected to be discovered with the Transiting Exoplanet Survey satellite are around M-stars. And this is just based on how the test, the Transiting Exoplanet Survey satellite, is set up. And so this is because where people are looking into these really because about 76% of all stars are M stars. And more stars obviously gives you more chances for a habitable planet. Also, planets around these types of stars are easier for us to detect since the ratio between the planet radius or mass to that of the star is larger due to the smaller stellar size. Additionally, the planets needs to be closer to the star for it to be the same temperature as Earth, and since M stars are cooler than the sun, and so additionally easier for us to detect if we see a dip in light every 2 days. M stars are also, they also live a very long time, and so our sun will be about 10 billion years old when it dies, but M stars can live to be about 600 billion years old, which provides far more time for life to develop. On the other hand, though, because the habitable zone planets are closer into their star, the planets may be most likely tidally locked, where one side is always facing the star, similar to how we see the same side of the moon always here on Earth. And this can cause one side of the planet to become very hot and the other to become very cold. Although life may not be able to live on although life may actually be able to live on the terminator, that kind of region where those two connect in perpetual dusk. M-stars are often known to flare a lot, and those flares release a lot of UV radiation that we talked about earlier. So kind of comparing these pros and cons, it seems that the pros do outweigh the cons for M-stars, but we really need to rank them in terms of what's actually important. And it seems that perhaps the cons may actually become a big issue. So not only do M-stars flare more often than our sun, but it's also been recently shown that they exhibit super flares, or flares with larger energies than the largest solar event ever recorded, and this happens every 1 to 10 days. So as I mentioned earlier, all this high energy radiation that comes from these flares may not actually be good for planetary life. So M-stars obviously have some big disadvantages. So what about the next step up then, the K-stars? In fact, K-stars might actually be some of the best candidates for hosts of habitable planets. So this group, Kunz and Guinan, in 2016 determined this parameter to essentially estimate the probability of a certain temperature of star to host habitable planets. And so you can see that this kind of peaks here from the late G to early K-star regime and remains quite high throughout the whole K-star regime in yellow here. And it actually remains above the probability of a G2 V star, which is what our star is, hosting a habitable Earth-sized planet. And so a higher probability, we say that is super habitable conditions. And so while this actually does peak in this late M-star regime, all this severe high energy radiation that we talked about may actually exclude these types of stars from being good hosts. So back to HAZKAT. We now know why we're studying the UV, and we now know why we're studying K-dwarfs. So let's actually get into the research a little bit. So for this work, I used UV data from the Galaxy Evolution Explorer, which was functioning from 2003 to 2012 and mapped about 2/3 of the sky. And I was also interested in X-ray, and so I used the ROSAT All Sky Survey, although I'm not really going to talk about X-ray results today. I'm going to just focus on the UV. What's really great about these is that we were able to do this whole project with just archived data, which kind of shows you the power of these types of surveys and that they can keep going for years after the mission is complete. So we got the data from the archive, but what we're really interested in is what is happening in the outer layers of the star, because this is where the UV and X-ray radiation actually comes from. And in fact, most stellar models completely neglect the chromosphere, the transition region, and the corona of stars. And so we really want to know what's happening out here. And so we actually did this work in terms of UV excess, which is simply the observed flux, or the UV flux that was observed with GALEX minus a stellar photosphere model. So this way we're just left with the flux from the outer stellar regions. And this is what we saw. So this is the UV flux as a function of stellar age. So the black points and red points here are observations, while the triangles are upper and lower limits on the observations. And the blue diamonds here represents median flux per age bin. So like this is the medium of all these points here, here, and so on and so forth. And so you can see here that there's kind of this region of constant flux out to beyond 150 mega years before it starts to fall off in both of these cases. And so notice the blue points here. And so I'm going to take these blue diamonds just in the FUV here for now, and I'm going to plot them on their own. In case anyone has noticed, the y-axis is, it's just been converted from flux density to flux. So that's why the numbers are different now, but it's still the same shape, still the same plot. So here's the far UV median flux for K-stars as a function of age. And here's what it looks like when we add in early M stars and compare it to early M stars. And by early, I mean spectral type M0 to M3, or the hotter, bigger M stars. They appear to remain constant at a they appear to remain at a constant flux for longer than K-stars before more steeply declining. And if we add in the late M stars, the M3 to M9, or the coolest and smallest stars that there are, then it actually remains at a constant flux for much longer and it doesn't really decline much at all. This is because these stars rotate much more quickly, and so they remain active longer. So these might look kind of different, but you can see that the difference is really only like an order of magnitude here. And so now I'm going to throw in the near UV results and also the X-ray results. And right now, you're probably thinking, wow, this is a super messy plot. Why would she ever show that? This is disgusting. Ugh. But that is exactly what I want to point out, that these are all right on top of each other. So the point here is that the intrinsic UV flux from the M stars is similar. They're all right on top of each other, the same flux values. But how much of that flux is actually getting to the habitable zone planets around those stars? Well, to look at that, we need to know where the habitable zone of each type of star is. So this is a plot of distance from the star. So your star would be right here as a function of age. Since your star is changing and evolving slightly during those beginning years and before it reaches the main sequence. And you can see here that K-stars in the black have a much larger and farther out habitable zone than M stars do, which are much more narrow and closer to the host star. So if we take those same median values that we saw before emitted by the stars in the last plot and say, okay, what would this look like at the habitable zone distances? Then you get this plot, which shows you how much average UV flux is incident on the planet. And you can see here that these are actually quite separated now. So the K-stars are consistently receiving, or the planets around K-stars are consistently receiving less UV flux at every age, especially compared to these late M stars here, the ones that were potentially the highest in that probability of habitability plot. So to summarize this HAZKAT data, so this was actually the first comprehensive study of UV and X-ray radiation from K-stars over these planet formation ages. But what we really discovered was that the absolute UV and X-ray flux from K-stars is similar to that of M stars. And the habitable zone planets around K-stars receive lower UV and X-ray fluxes than those around M stars. And this is because of the farther, wider habitable zones of the K-stars. And so lower UV flux is probably better for life. So that's probably good, right? Okay, let's take another Zoom poll and see what you guys are thinking now about K-stars. Tom?
Same poll?
Yes, same poll. It's always going to be the same one.
Okay, let me see if I can.
Hopefully it resets. I didn't check that.
I might be able to try and duplicate that poll. Are people seeing it? Let's see.
I'm not seeing it quite yet.
A relaunch poll.
Yeah.
Yes, clear existing data.
Great. Okay.
Yes.
Yep, there it is.
Hooray. Oh.
I'm not gonna bias anyone's by saying what the current numbers are.
So tell me when to end the poll, and then there's a button I can click to share the poll.
Oh, okay. Yeah, I'll tell you when to end it. So it seems like it's kind of stalled. So now, remember before it was about even about a third for each of them. So now we have 19% for solar type stars and 72% for K stars and only 9% for M stars. So I see that I'm convincing you guys to K door. So now let's see what happens next. All right, Tom, you can end the poll. Thank you.
Did that disappear?
Well, I also closed out of it. So
Oh, okay. Yeah, I don't see it either anymore.
Okay, great. Okay, and so the HAZKAT results were a really good general start to this work. However, GALEX data is photometry, that it's broadband, so all of these wavelengths kind of shoved into one observation, and they only give you a general picture of what's going on inside the star. So instead, what we really need is spectroscopic data. So this is a spectrum of flux versus wavelength, and each of these lines here traces out exactly what is happening in different locations in the star. For example, in the NUV, the magnesium-2 line here has a peak formation temperature of 10 to the 4 Kelvin, and so it is formed in the middle of the chromosphere here, where the temperatures are about 10 to the 4 Kelvin. And the FUV mostly traces the upper chromosphere and the transition region of the star. So by understanding the evolution of these specific lines, we can see the evolution of the different stellar regions. And we've seen in previous works from my team that the UV evolves considerably between young to field ages. This is an example for M stars from Park Lloyd, and we see that the surface flux density evolves by multiple orders of magnitude for M stars, which definitely plays an effect on planetary atmospheres. But at this point in time, there wasn't any spectroscopic UV evolution studies yet of K stars at these early ages. And so obviously I was all over that. So I led an HST proposal with some awesome collaborators at Arizona State, University of Arizona, and University of Washington. And we were awarded 73 orbits to study K-stars at these different ages, both in the near UV and the far UV. And so our goals broadly are to spectroscopically study the evolution of the UV radiation, determine the frequency of flares, and to model the extreme UV, which is mostly unobtainable for stars other than our sun, but is really important. And so today I'm going to talk about the results from my first point here, since this is what I just submitted a recent paper on. Actually, I got an email right before this talk that said it was recommended for publication, so that was super awesome. Yeah, so here are 3 examples of spectra of stars at 3 different ages. And so these are now K-stars. This is our real data. And so we can see here that unlike the M stars that I showed before, the K-stars don't appear to evolve much at all from 45 to 625 million years. And so as well as comparing the broadband characteristics of the spectra, we also want to look at specific spectral lines that probe the chromosphere and transition region of the stars to see how those evolve in time. So if we take magnesium-2 here, for example, we can measure the surface flux from the line and plot this as a function of age. So these flux evolutions are typically presented as a region of constant flux, followed by a power law decline. Here we can see that for magnesium-2, this decline really isn't that sharp, but it's there, and you see that there is kind of this constant flux out beyond 650 million years. So other than magnesium-2, we have done this for 7 other spectral lines in the far UV, as well as the near UV and far UV continua. So I don't want to overwhelm you with a ton of plots, so I've just plotted a subset of these here. I should note that there are actually multiple points here. They're just all kind of on top of each other. And you can see that they follow the same trends that we saw in the magnesium-2 and the broadband spectra. And so you have this period of constant flux again out beyond 650 million years, followed by a decay. But what's really, really interesting is that when we compare this to M stars, we see that the K-dwarfs actually appear to have a prolonged saturation period as compared to M stars, which fall off by only a couple 100 million years old. So the K-dwarfs actually radiate more UV flux at these intermediate ages than do M stars. And while the evolution of M stars is pretty well known and constrained by these, the age at which K stars actually do begin to decline and UV activity is still really unconstrained. Like all of these are different potential ages where that kind of knee could be. And another important factor to look at, though, is how the UV changes with rotation period. So here I have plotted the Rossby number, which is the rotation period divided by the convective turnover time for those stars in our sample, which have rotation periods. And if that's confusing, you can just think of this as rotation period. Valid. Now you're probably waiting for me to bring up that red line to show you the comparison with the M stars, but it's actually up there already. The K-dwarfs and the M stars show nearly identical UV evolution with rotation. So that's kind of weird. Like what's happening here? What does that happen? Well, we think that this actually might be related to this recent K-dwarf rotational stalling effect. Seen by this group, Curtis et al. 2020. So this is a plot from their paper that shows rotation period as a function of stellar effective temperature for stars in different clusters at which all are different ages here. So overlaid, you have current gyrochronological estimates of where we'd expect stars of that age to fall within this rotation period versus temperature plot. And you can see that these lines match up pretty well for G-dwarfs here, and that there's some clear rotational evolution from 670 million years to 1 gigayear for G-dwarfs. However, so like this rotational difference is the fact that this orange and green lines are not on top of each other. But for the K-stars here, they are on top of each other. We see no rotational evolution from 670 million years through 1.4 gigayears. And so this is an effect that they're calling the K-dwarf stalling, where the rotation spin down of the stars actually stalls. And so this rotational stalling might actually be what we're seeing in this UV temporal evolution stalling of K-stars, since we know that the rotation is tied to the magnetic field and therefore the magnetic activity of the star, or the what's coming from the chromosphere, the UV. And with this rotational stalling, you wouldn't expect to see any distinct differences in the UV evolution with rotation period, even though you would see a difference with age. And so that's exactly what we see. So we think it might be this K-dwarf stalling phenomenon. So to summarize this HST data, the K-dwarfs appear to experience a prolonged period of saturated activity compared to M-stars, which may be due to this rotational spin-down stalling. And additionally, the HST program is going really well, which is really good. And for these other goals, this is what I'm hoping to work on in the future. So stay tuned someday for that. So kind of reviewing what we've done so far, HAZKAT showed us that K-stars have similar UV fluxes to M-stars, but the HST work showed us that K-stars have a higher UV flux. So how does that work? Like, that's two different answers. That doesn't make sense. And so I actually decided to revisit the original HAZKAT data. So something I kind of glossed over before was that this data was all done in forms of proxies for distance. We didn't actually have the distance measurements back then. Yeah, so back when this work was originally published, we didn't have any of this new data from the Gaia mission. And the Gaia data, I'd say, has been some of the most ambitious and driving work of current local astronomy. It's really revolutionized our data and our ability to analyze that data. Gaia's job is to provide a 3D map of the Milky Way and to measure the motions of stars. And so with this new data from Gaia, we now know all of the distances to our stars, so we can make more precise measurements of what the true radiation from these stars actually is. And so I redid the HAZKAT project now with these updated distances and got drastically different results. Well, for one, we learned that the distance proxy we used probably wasn't the best, but it was the best we had at the time. But more importantly, these are the same plots that I showed before, the ones that were overlapping. And so here you have the median UV flux as a function of age. So instead of all being overlapping like they were before, there's now a clear distinction in which K-star, the diamonds here, intrinsic UV flux is an order of magnitude larger than that from M-stars in both the far UV and the near UV. And when we turn this into the flux that would be incident on the planet in the habitable zones, then we now see that these fluxes are all overlapping. They are not that nice, clear separation that we saw before. So what we've learned is that there actually isn't a big difference in the UV radiation between K-star and M-star habitable zone planets. And so in conclusion, the work that I presented here has been some of the first UV studies of K-stars as a function of age. And in this process, we found that K-stars are super weird. They exhibit a prolonged period of saturated activity that isn't seen in M-stars or G-stars, although I didn't show those. And when you look at the flux incident on a planet in their habitable zones, the K and M stars do receive similar quiescent fluxes. So just the flux that is naturally coming from the star. And so what's really going to make or break it for this question of K-star superhabitability is whether they exhibit lower flare rates than M-stars do, since these flares can also eject a lot of UV energy. And that's what I'm hoping to do to study next as a postdoc somewhere, hopefully. Yep. And so with that, I'm going to put up our poll for a final time to see what you guys say, and then I will take any questions after that. Thank you, guys. let's do this final poll. See what you think now. I think the last K-Dwarf numbers were 73%. Is that right?
Let's see.
Still, the K-Dwarfs.
Yeah, do you see the old ones?
Yeah,
Yeah, there's the old ones. Let's see, I thought I duplicated that poll.
Okay, I think I can
Let's see,
relaunch.
I have to relaunch it somehow. Let's see.
Here, I think I can.
Oh, there we go. Oh, did you see it? Yeah, relaunch. There you go.
All right. What do you think about K-Dwarfs now? I guess.
I think I would have stuck with M's or G's. I mean, G's. Sorry.
And I think most people are doing that. So
yeah,
about 63% in, and yeah, so it's about wait, that's 50.
it's close.
I don't understand these numbers. 50, 50, 12.
I'm seeing 25, 20. Okay, they're changing 26G, 25K, 6M.
Yeah, so about 48% G, 46% K, and 11% M stars. So yeah, it's been very interesting to see. Yeah, so that was kind of like my thoughts as well. Like at the beginning of my PhD, I was kind of like, okay, like K-stars are cool, but probably M-stars. And then I started to learn more about it. I was like, K-stars are the absolute bomb. Everyone should study them. They're the best. We're going to find life around it. And now like, let's see what the flares say. And so it seems like you guys are in the same situation now. And so it's been really interesting to see that. And I hope you learned something about K-stars from this talk.
Well, thanks, Tyler. Yeah, if you have some more questions, please put them in the Q&A. Yeah, that's pretty scary with those flares going off every 10 days.
Right?
Yeah, I can't put on enough sunscreen to protect from that.
Yeah, exactly. Not super great for, fair redheads on that planet.
Right. Yeah, live on the backside or something. Okay, we've got our first question. Why was I only seeing G?
Oh, there, I see. Was that in terms of the poll?
Hang on, let me enable
Yes.
David to ask his question.
Mm-hmm.
It's gonna take a couple clicks. Got too many windows open. Okay, hang on, it's coming. Okay, David, you should be live. You can ask you can unmute yourself and ask live. Okay, maybe when we can come back.
I've got it this way. Each time that I saw the poll, the only choice I had was G.
Oh, I'm sorry.
I was not seeing the other two options.
So maybe
So I punched G every time because that was all I could see.
our poll was a little biased, but I'm sorry I haven't had that happen before. But that's good. That's good to know in interpreting those poll results. So thanks.
I assume some people had all three.
Yeah.
Just not me.
Oh, that's odd. Sorry about that.
I knew this next question. So.
Yeah, let's see. Tom Harvey, you can go ask your question live, please. Takes a little bit.
I'll read it out while he's working on it, and then maybe.
Sure, go ahead. Yeah.
So the question is, why do M stars and K stars, or why do M stars, which are cooler, emit more? Why do the M and K star cooler emit more UV? So I might actually need him to explain. I think what he's asking is so the case. So actually, let me make sure that it's what if he's there and can ask that question. I think I would prefer clarification.
Is that because they have less mass to hold their stuff together?
So, and it's also there is a difference between I think a lot of people think like, okay, so the K dwarfs are hotter, and so their black body flux is more geared towards the UV, and so there should be more. But so why did the M stars sometimes appear to have more UV flux than the K stars? And that is actually because the chromosphere and the transition region in the corona do not actually follow a black body, and so they don't actually go hand in hand with that assumption, just because we don't really see any of the continuum, only very small amounts of the continuum in the UV. It's really all these emission lines. And so there's more emissions in the M stars. So that's really what it comes down to. Hope that answered that. Oh, okay.
You should be able to ask your question, Derek.
Oh, hi, can you hear me?
Yes.
Oh, hi, Tyler. Excellent talk. Thank you. Very informative. My question is where is or how far away is the closest K star that we've detected? And do we know if there are any exoplanets?
That's a good question that I don't actually know off the top of my head. I'm happy to send you an email though about it. And so in terms of, I'll just talk more broadly about how many like habitable zone K stars there are and if they're like close to us. So currently we don't know of too many, but I think that's mostly just because the missions have really been set up such that we only find out about M stars. And so there is actually going to be a telescope, Plato, which is a European Space Agency mission, which should be launching in the next few years, I think, which is going to be specifically looking for habitable zone planets around K stars and is expected to find about 30 of them. And those are all going to be around nearby K stars. And so maybe definitely within 50 parsecs, I would say. So maybe not feasible for us to travel anytime soon to those, but nearby.
Like over 100
awesome.
light
Thank you.
years. Go ahead, Rick.
Okay, so out of the current suite of spacecraft we have out there, what do you think is going to be the best for studying these M-star flares?
Yeah, that's a great question. So I'll tell you that for the M-star flares, Hubble is actually not great, just mostly because they're worried about the saturation, or they're worried about these flares being so bright that they destroy the detector. And so really, okay, currently the only way to study these UV flares is with space missions.
Right.
Since the UV is absorbed by Earth's atmosphere. And so you have to be in space in order to understand the UV. But there is actually upcoming missions. So there's CubeSat, there's a CubeSat called SPARCS, the Star Planet Activity Research CubeSat, which is going to launch next year. And that's actually going to stare at these M stars and some K stars for actually like a month at a time to get a full idea of like how often flares at certain energies occur. So it's really more upcoming. People are just now really starting to think about M-star flares and flare activity and what that actually means for habitability. And so that's really going to be a future thing that's happening. But we're working on it, so.
Good. Good luck with that. Hopefully you get involved with that.
Yeah, I really hope so.
Okay, thanks.
Okay, and Tom Curry doesn't have a microphone, so
Okay. So his question is, so should there be a sufficient atmosphere to develop over time on a K-star? Could the tidally locked potential of the star be the saving grace for any life?
And later on, he said he meant the K-star planets.
Yeah,
Yeah.
I do the same thing, and I catch myself every time. Oh yes, I see that. I guess the question is really about the lifespan of K-stars then, or the first part of the question. And so, I mean, so the K-stars live about not quite the 600 billion years like the M stars, but longer than our 10 billion years. I think it's maybe more like 80 billion years. Don't quote me on that exact number. But still, like Earth, like we've have life formed, obviously within the 4.6 billion years that we've been here. And so there should be plenty of time for life to develop. I think it's really with longer stellar lifetimes, you get more of a chance to probability. Like life doesn't have to start exactly at the beginning when the planets just form. The atmosphere's great. It can be a little bit later if you have longer stellar lifespans. And so for the second part of the question, could tidally locked potential of stars or of the planets around the M or K stars be the saving grace for any life? I do think so. So I think it's really on those terminator regions. So like I guess those planets could be the ones that are really close in, potentially not actually in the habitable zone, but maybe even closer into the star. So you would get even cooler regions on the backside of the star, or excuse me, the backside of the planet, just because it's never coming into contact with any solar radiation. And so you actually may get some habitable conditions there just because it's the right temperature, even though it's not nominally in a habitable zone. So yeah, great question.
So I accidentally said Steve's question was answered, but it isn't. So Steve, can you unmute yourself and ask your question? If you look in the answered questions, there was a question.
So
Like how could you tell if the K-star has a magnetic field?
yeah, so the K-star planet, yeah. That's a great question and something that we're always asking in our field, but what about magnetic fields? And I've caught myself asking that myself. And so yeah, so that is really something that really could be the saving grace for some of these planets that are getting a lot of UV radiation, whether that's from M or K stars or G stars. And so like Earth has a magnetic field, and that's really helped protect us as well. And so the way we're working on directly measuring magnetic fields. So there's kind of two ways that we're considering that people are considering right now. I shouldn't say we, well, I'm doing one of them, but so there's really on the radio side of things, people are working on looking for auroras like the northern lights on these planets, and in the radio, there's a property of the auroras that the magnetic field strength is directly related to the wavelength at which we observe these auroras. And so we can tell exactly what the magnetic field is that way. The problem is planetary magnetic fields are so small that we've never been able to measure them specifically on ground, because you have to have really, really tiny or really, really small low frequency wavelengths. And so that's something that people are working towards, but there hasn't been a direct observation of that yet. And then on the other side of things, you can get some essentially magnetic modulation within the star from your planet with a magnetic field going around the star. And so that actually has been detected before in only a few cases of just some calcium 2H and K lines specifically, it's what they are, kind of just getting modulated as the planet rotates. So great question. That's something that everyone really in the field is super interested in. We're just really working towards getting the ability, the sensitivity to observe those things yet. Not quite there, almost. I'm willing to bet in the next decade we'll get some more direct measurements. So,
Okay. Did you answer Tom Curry's follow-up question about tidally locked?
yes.
Okay. Yeah. And then Woody can ask his question live. He actually takes spectroscopic data in his backyard of various stars. So go ahead, Woody.
Thanks, Tom. Hi. I'll just read my question, but we have a group studying late K stars and early M stars to determine FFDs and flare energy levels using both photometry and spectroscopy. But we're ground-based using small telescopes, which means we have to work in the optical spectrum. The question is, do you work in this portion of the spectrum? You talked about near ultraviolet and far ultraviolet.
Yeah, so actually, that's what I'm working on my NASA postdoc position research proposal on, is actually kind of making these connections between optical and ultraviolet. And optical observations are really important. We are getting a lot of those from the ground as well, or like TESS is optical. There's also like every scope is a telescope that stares at the sky. But yeah, so these optical flares are really important, but they don't quite tell us the complete picture. So we've actually seen recently that for every, I guess I shouldn't use specific numbers since we're not sure, but say you get 10 flares in the optical over, well, let's go, it's 5 flares in the optical, that might actually be double in the UV. So there's some sort of misconnect or where the flares from the UV are not actually fully manifesting as well in the optical, or maybe there's just not enough sensitivity right now. But
so we've been looking at, because we're stuck in the optical being ground-based, we've been looking at the Balmer lines. And we published a paper on AD Leo, which is an M4 star.
right.
And we actually saw quite a few flares. But interestingly, they were represented more strongly in H gamma, less in H beta, and even less in H alpha. And we've been working with Dr. James Jackman.
Oh, yeah, he's actually in my research group. Yeah, he's a great person to work on that with. He's actually, when I mentioned these disconnects, he's actually working on that right now.
Excellent. So we've been working with him, or he's been consulting with us, or I guess helping us, guiding us. So we've also been looking at late K stars, and we've just recently completed a study of BY Draw, which is a K4 star. But is pretty tough because the flares are quite infrequent as you move to hotter stars. And so we're going to be working EVAC next as a group. So we're very interested in the presentation you gave tonight, and it fits really right in with the work that we've been doing with Dr. James Jackman. Thank you.
Yeah, and I really don't want to discredit the optical. Like optical is super great, and like honestly, just comparing the difference in what we see between the optical and the UV is really important to understanding like how these actually flares, or excuse me, how these flares actually manifest. And so I think that's really valuable work. So thank you. And I'm actually, if you don't mind sending me that paper, I would really appreciate it.
Okay.
I think that wraps up the questions. I don't see any more in the chat. In chat, there's a bunch of kudos, so nice job.
Thank you. Oh, I see. I love that dog. I assume that was my life picture with my dog.
Yep.
Yeah, I was trying to figure out how could I put a picture of my dog in a research talk. So
Cool. And I think that's it. Okay, so yeah, thanks, Tyler. And we'll hand the meeting back over to Gordon.
yeah,
All
thank
yours, Gordon.
you. I really appreciate it.
Hey, there I am. I'm back on board with everybody. Tyler, thank you very much. And what a great presentation from our younger people, and about all the different things, all the different aspects about astronomy that people are unaware of, that our young folks are diving in and getting their PhDs on. So, Tyler, I'll have to ask you, is that when later on, we will have to ask Dr. Tyler to come and give us an update on what your findings are, okay?
Absolutely. Anytime.
Good, good, great, great, great. So next meeting is on the 19th of November, and Jeff Knipe will be talking about peculiar galaxies. That's something we don't want to miss. That's well, that's a catchy title, that's for sure. 19th of November, 7:30, third Friday of the month as usual. It looks like our holiday party, EVAC holiday party, is not going to happen. It usually happens instead of a December meeting, we have a holiday party. Doesn't look like it's going to happen. So we should just kind of assume that it is not, unless something dramatically good happens. And remember, officers, folks, if anybody is interested, let me know. We only have until Monday. So anyone who wants to be involved in this great club that we have in our transition next year into back the way we were, we have a lot of people in the club excited to jump in and help out with outreach programs and some classes that we had that we were going to start before the pandemic. So if you want to be a part of that leadership team, join us. Email me. I'm interested in whatever. And see us into the year 2022. So, that is it from me. Tom, do you have anything else?
No, I'm good.
Oh, let's see. We got two more chats that came on in. Oh, yeah, basically just kudos. Yeah, great. All right, Tyler. Again, thank you, and looking forward to hearing from Dr. Tyler.
Thank you all so much for having me. I really appreciate it. The chance to speak.
Okay, good. Good, great.
Yeah, you had a near record turnout. So
Yeah.
Congratulations.
Wow.
Yeah, we're up to 90, 91, 92, something like that.
I have 91.
Thank you all so much for coming.
Well, as usual, gang, I will give the countdown for the end of the meeting, and I will see you on 19th of November. 3, 2, 1. Bye, everybody.
Bye.